Hello, my name is Adrian Steen from the University at Buffalo, and here I will briefly talk about multi-resonating metamaterials. Local resonant band gaps are widely known for their strong attenuation, but yet for the narrow frequency spans. During this presentation, I will describe the behavior of acoustic metamaterials, where unit cells house multiple resonating elements which can be stacked in series, parallel or hybrid configurations. In its simplest form, a 1D acoustic metamaterial with parallel identical resonators can be modeled as a series of lump masses MA, which are connected to each other by springs of stiffness Ka and house multiple resonators of mass MB. The dynamics can be represented by the displacements U tilde, V1 tilde and VR tilde. K tilde is a normalized wave number, while omega B is the standalone natural frequency of the resonators. Performing a row reduction on this system leads to the reduced dispersion relation. From the free wave solution, the normalized frequency can be now plotted over the normalized wave number, as can be seen here for R equal to B1. The bounds are located as follows. If we add one more resonator in parallel, we can see that the lower bound shifts downwards where the upper bound shifts upwards, resulting in a bandgap widening effect. Furthermore, we can see a flat branch, which is indicating that there's a local resonance mode. If we continue to increase the number of resonators to be 3, for instance, the widening continues. Analytically, we can write the lower and the upper bound as follows, which only depend on normalized parameters, which depend on the spring stiffnesses, the masses, and the number of resonators. Consistent with a single resonator metamaterial, the upper bound is independent from the spring stiffness. The unit cell modes are obtained by casting the dispersion relation as an eigenvalue problem and solving for the eigenvectors, or one could say, by calculating the null space of the left-hand side of this equation. For R equal to B1, the acoustic and the optic mode look like so. When R is equal to B2, we can see an acoustic mode, a local resonance mode, and an optic mode. When R is equal to B3, remember we have two coinciding dispersion flat branches, which results in two local resonance modes, as can be seen here, and an optical mode. Irrespective of the number of resonators, the outer cell is only oscillating in the acoustic and the optical mode. This whole behavior can be generalized with a block wave mode matrix, where the middle columns describe nicely the displacement in the local resonance modes and can be illustrated with an identity matrix, for instance, which only depends on the number of resonators. The first and the last column are the acoustic and the optical mode. A question that can be asked now is, since we stack resonators in parallel, does this always mean we need a heavier metamaterial in order to achieve a bandgap widening effect? The answer is actually no. From a practical standpoint, the overall mass of a finite metamaterial is a function of the total number of unit cells, and therefore it cannot be evaluated with the unit cell analysis. For this reason, let me introduce you metamaterial A with 12 unit cells where each cell houses one resonator, and metamaterial B with 4 unit cells where each unit cell houses 3 in parallel stacked resonators. It should be mentioned that all resonators have the same parameters and that the total resonator mass is the same in both metamaterials. Let's look at the frequency response. At first glance, it seems metamaterial B has a wider bandgap than metamaterial A. But how can we quantitatively compare the bandgaps in the best way? First, we can define a size-normalized bandgap width, where the difference of the upper and the lower bound gets divided by the number of unit cells. Here, metamaterial B shows a 714% increase compared to A. Or second, we can define a mass-normalized bandgap width, where the difference between the upper and the lower bound gets divided by the total mass. Here, metamaterial B shows a 457% increase compared to A. From a transfer function perspective, poles and zeros play an important role in the formation of local resonant bandgaps. Poles represent the peaks and sit at the lower and the upper bound, while the number of repeated zeros defines the bandgap's strength. Looking at metamaterial A and B, we can see that 12 zeros are sitting at 1, corresponding to the 12 resonators we used in both metamaterials. However, since we introduced a parallel stacking of resonators in metamaterial B, we can see that the transfer function created poles sitting at 1 too, resulting in some pole zero cancellations. In B, the peaks at the lower and the upper bound are further apart, resulting in a bandgap widening effect. With this in mind, we are able to design more compact metamaterials, which can be used when sensitive size constraints apply. And a bonus added to that is that there are less resonant peaks, as it can be seen here or here. With the structural dynamics approach and the mathematical manipulations, we are able to derive the closed form expressions for finite metamaterial for the lower bound and for the upper bound. The idea was put into a 3D model environment in COMSOL using a free-wave approach. The aim is to show that the bandgap widening effect extends to continuous structures. Therefore, a periodicity in Y and in X has to be taken into account. In order to show you how I designed the internal resonator, let me slice the outer cell. For one resonator it looks like so, and for two like so. Let's take a look at the dispersion diagrams of the two different types of unit cells. When R is equal to B1, we can see two bandgaps evolving here. But we are more interested in the lower bandgap. The blue curves are the out-of-plane modes, and the dashed black curves are the in-plane modes. The first eigenmode is an out-of-plane mode, and looks like so. The next eigenmode is an in-plane mode, and looks like this. And again, the third eigenmode is an out-of-plane mode, which looks like this. When R is equal to B2, we would like to see that the bandgap widening continues. And this is indeed what happens. And the animations look like so. With the addition of more resonators, we are also able to see the flat branches, which represent the local resonance modes, similar to the spring mass system. The resonators can be stacked in a series configuration as well, as it can be seen here. And it should be mentioned that the resonator parameters are still all the same. If we, for instance, choose the number of resonators R equal to B3 and the number of unit cells N equal to B2, to B4, to B7, and to B10, we can see the following frequency response. And as expected, because we have three resonators, we see three distinct bandgaps occurring. However, no bandgap widening occurs. What if we hold the number of unit cells N equal to B10 constant and vary now R equal to B1, to B3, 7, and 10? Let's have a look. So for R equal to B1, we know that there's one bandgap. But for R equal to B3 now, we have three bandgaps, and for 7 bandgaps, and so on. So stacking resonators in series is merely a way of introducing new bandgaps at distinct tuning frequencies. But how about we combine the best of both worlds? So let me connect the ideas between the parallel and the series case. This results in a hybrid configuration and allows us to place bandgaps at specific frequencies and widen them at the same time. The number of resonators in a series configuration are named by Rs, the number of resonators in parallel by Rp. So the whole number of resonators is just the product of Rs multiplied by Rp. If we, for instance, now hold the number of unit cells equal to B10 and the number of resonators stacked in series equal to B3, and we just vary the number of stacked in parallel resonators, we get the following answer. We see that three distinct bandgaps evolve, which makes sense because we have three resonators in a series configuration. While all of them widen, we can see, for instance, that the last bandgap widens a lot more than, for instance, the first one, which is due to the constraints which are imposed on the first bandgap, which cannot widen as freely as, for instance, the last bandgap. To conclude, stacking resonators in parallel has several advantages. One, for instance, is a downward shift in the acoustic mode and an upward shift in the optic mode, resulting in a bandgap widening effect. It should be mentioned that with every stacked resonator in parallel, we introduce a new local resonance mode. But it could be seen from the frequency plots that these do not interrupt the bandgap formation. So the main advantage is actually a more compact metamaterial when we stack resonators in parallel, and which has the same or better functions, namely lesser resonant peaks over a given frequency, a wider bandgap, and lesser material. Stacking resonators in series creates new distinct bandgaps. So combining the series with the parallel idea results in the hybrid configuration, which allows us to selectively place bandgaps at specific frequencies and widen them at the same time. So what we get are multiple widened bandgaps, which can be useful for a number of applications. Finally, I would like to acknowledge the US National Science Foundation for their support of this work. And for more detailed proofs and further discussion, I refer to the following manuscript. Thank you.